All right. Hello, everyone, and welcome to part 3 of this stream, where I'm going to attempt to finish solving this crackme by Antonio Parata, also known as s4tan. So let's start with a little bit of a recap for those who missed the first two parts, and then let's jump back into the action. So some time ago, Antonio Peretta posted this challenge on Twitter with a link to the GitHub page, and the challenge is a classic crackme challenge. So we get in this case, a Windows executable, and we are supposed to find, first of all, a valid ID and license pair, and then just generally be able to create an arbitrary number of licenses. Basically, we want to reverse the verification algorithm and understand completely how it works. So how far along are we in this? Let's bring up the materials we have so far, and I will explain what we have done and what's left. I'm also going to open another instance of IDA. And please let me know in the chat if there are any issues with the audio or video or anything. Also, if you have any comments, questions, suggestions, and so on, yeah, please write in the chat. Okay, so let's start from the top to make this clear. So we have this program. I will just go through this briefly. If you want to see the details, watch the previous two parts, which are available here on my channel. I will also put links in the description to easily find them. Anyway, the program, it asks for an ID, and then it reads the ID, and then it asks for a license key, and it reads the license key. And I think we also figured out that it saves the length of the... Yes, here, it stores the length. I think this the return value here is the length of the license key. We haven't fully verified that yet, but I'm pretty sure that's it. It stores the length of the license key, and then it makes the whole code segment writable. And then it looks for certain marker values in the code. There are two sequences of 16 bytes, which it finds and it stores into global variables. So these two global variables, it will store the location of this sequence here. And then, like at the end of this block, there's another such sequence down here. Yes, here. So basically, it locates the start and end of this block, which contains encrypted code. So where were we? Then it will say that it's validating the license, and then it will do some trickery here where it switches from 32-bit to 64-bit code. And essentially what this does, it initializes a global variable. We should actually open up, we have this code disassembled in Binary Ninja. Let me go there. just it will initialize this global variable here will be initialized inside here, because it switches from 32-bit to 64-bit mode here, and then runs this code and will initialize this global variable with one of these two values based on this value, which is inside the PEB. I don't know what this value is, so I don't know exactly which one of these two values will be chosen, but we can easily check that in the debugger or something. We haven't come across where this is used yet, so we don't really know. But anyway, it does that. Then it sets up a structured exception handler, which I will cover soon. It activates this flag that we are inside of this thing that will be covered by this exception handler, and then here it turns on single step mode, so that after every instruction it will raise an exception, which will be handled by this exception handler. Then it calls this function with the license ID and key as arguments. So, and afterwards a few other things happens, and then it's decided if the inserted license is valid or not. And then if we look at this location of this verify license thing, this is actually garbage, and if we try to interpret this as code, it doesn't make sense. So what happens is that in this exception handler, it will decrypt. So for every instruction, it will decrypt. First of all, it will restore the previous ciphertext of this, if there was anything decrypted previously, and then it will decrypt the next instruction. And basically the decryption algorithm is that it sets up a table of 10 different small functions, which are small decryption things, which will take basically the address of the byte and the value of the byte and combine them in different ways to create a new value. So it will set up a table of 10 of those functions, and then we'll start at one offset in this table, and it will go around. And when it has used all the functions, it will like reinitialize this table and continue looping like this. And it will do this for 15 bytes because the maximum size of an x86 instruction is 15 bytes. So if we decrypt 15 bytes, we know that we have decrypted enough to fully decrypt the next instruction. And then it will execute this instruction, and it will go to the next exception, which will restore the previous ciphertext, decrypt instruction, and so on. And what we did last time is that we re-implemented this. I'm going to increase the font size a little bit. We re-implemented this whole decryption algorithm in Python. And we used the debugger in this Windows virtual machine to find some bugs with the implementation, and I correct it. And then we basically decrypted the whole this whole block in one go, and created a new binary where we like hard coded in this this decrypted code instead of this the encrypted code. And then we can look at this code here, and we can go to the verify license thing. And here instead, there's another trickery going on, because here it looks like it's using this in instruction, which you basically don't see. I mean, it's a real mode thing, so you basically don't really see this in normal programs anymore. But this is misleading, because calling this will trigger another exception, specifically this one, which will then go into this function here, where it will basically act as a special function call thing, where this in function consists of 2 bytes, E4, and then a number. So this number will act as a index into this table. And this table is a table of function pointers to these decrypted functions. Let's see if we can go to this table in this version of it. Yes, here. So here's the table. It's right after these markers. So inside of the exception handler, basically, so all of these should not be interpreted as the original intention of the in instruction, and instead be interpreted as call the function with index, in this case 5, index 5 in the function table that we have here. And if we look at these decrypted functions, we have a bunch of them which look like this, where it will call one of these functions. So like all of these functions look like this, where they will call various, so they will do something in the beginning here, and then it will call another one of these functions based on the value of the... Oh, interesting. Based on the next license, next value in the license. So let's see what happens in the end, actually. Right, so it will do this, and then it will call one of these functions based on the license key value, and then this will lead to a whole chain of executions, and then at the end it will call function number 3 here. And also this looks much more nicer. Like if we look at it here, it looks like a nice switch statement. So it's basically taking like the current value of the license pointer, and it's basically a switch statement. And actually you can see this else case here is also, if we think about this, it looks at like if the current value is not 0, it will do this switch case, and otherwise it will do this case here. But we could just think about this as being another case in the switch statement, case 0 instead. So all of this is just one big switch thing, but then finally it will call this function number 3 again. And I think in the other functions which have this structure, it's like the same thing. So they all have this very strange form like this. But if you think about it, what it's actually doing here is it's first looking at the it's taking this is the current license pointer. So this would be the value in that position. And if it's not 0, we will go into this thing, but let's look down here instead. If it is 0, it will do this. And then it will take this value -1 and repeat the process. So it's essentially checking if the initial value is 1, and then it will do the same thing again. So effectively checking, is it 2, and so on. So this whole thing could have been much more nicely decompiled as a switch statement instead of this messy, like nested, these nested if statements. So this is essentially the same thing here as here. I wonder if the indexes are the same though. So for 0, it calls 4, and then like 5, 8, 9. Let's, for example, compare this here. So for 0, it is 4, and then it would be 5, 8, 9. We kind of read this backwards, so like from the outer. So it looks like it's using kind of like the same switch statement throughout. Which is interesting. And then you can see what these functions actually do. So I mean, the beginning of the function is like the actual part that actually does something. So this looks like it's, you know, shuffling around a bunch of elements in some array. So there are basically 2 ways we can go about this, or I guess 3 ways we could go about this. Either we kind of like just keep the code and the decompilation as is, and we just mentally do this translation with the calling, since in this case it's not actually terribly complicated. We would just have to like cross-reference the table of functions. The other thing we could do is to like modify the program, or at least modify the decompilation to actually properly interpret these as function calls, and then, you know, maybe all of this becomes much more readable, and we get some clarity from that. And the third way would be to just simply actually run this in a debugger and you know, observe how the license is manipulated, and see if we get any insights from that. And I think it would be interesting to try to actually, you know, make this look better. But we can start first. Let's see if we can get some like easy wins here by basically we want to look at what the return value of this verify license thing is. Actually, that's not really true, because we should take a step back here and think about what is this return value used for. Oh yes, so another thing we noticed is that at the startup of this program, it installs, let's see, where is the entry thing? Oh, it is in the start function. So was it there is some place in the code where it installs this like IO. Okay, so inside this function, which is called, oh, it's actually called afterwards. Okay, so this function here installs this IO proc thing. So it's like it hooks some IO processes, like this MMIO hooking thing. I know pretty much nothing about this, but essentially it's like a hook. So on different like IO commands, like reads and stuff, you can do things. So basically what it's doing is you have this huge block, like this whole, like if you look at this whole composition here of the program, the actual code is just this little thing here, and then we have this huge block of data which is accessed through this IO proc thing, which so it's basically, it looks like this is kind of like a virtual disk thing, and this global variable is actually the size, and it matches actually the size of this data. So here we should call this like setup MMIO proc or something, which is called here. So we see here that this okay, that was a big cost. But anyway, the return value here is used to call this function, which we haven't really looked at. Oh, this looks like some kind of encryption or decryption function. This looks very much like the setup of an RC4 function. Let's so Antonio says that that is correct. So I'm just going to explain how why I think that this is the case. So this is actually very interesting. Like identifying cryptographic functions is like a very good skill as a reverse engineer. Usually, like most cryptographic algorithms have some kind of they have various constants that you will find. Maybe it's some start value or something they like multiply with in like every iteration, or some kind of constant. And these constants, like if you Google these constants, you will end up you will find these cryptographic algorithms. RC4, however, is very interesting because it doesn't have any of those constants. You see, there is like, I mean, sure, there's a 256 here, but that's like an extremely generic value in computing. And it's just like an iteration count here. So RC4 you have to identify by its structure. And RC4 works in 3 steps. First, you initialize, you have a table of 256 elements. You initialize it with the values 0s to 255, which it looks like it's doing that here. Just need to double check this. And then you have the key scheduling, where you have a loop where based on the key, you shuffle around, you swap these entries in this table around. And then finally, you have the actual key stream generation and the decryption, where you continue swapping these entries around and at the same time XOR with the plain text or the ciphertext, depending on if you're encrypting or decrypting. So this is why, to me, this looks very much like RC4. Actually, I can actually point out, I wrote an article in Paged Out. Was it in the first issue? This is a great, what do you call it? A technical magazine created by Ginwell and some other people. Only released 2 issues so far, and the third one is a little bit delayed because, you know, the state of the world and so on. But in this, I wrote an article about, yes, here in the second issue, I wrote an article identifying crypto functions, where I'm talking about these things, and I'm talking about RC4 as a special case. And so, you know, if you want a slightly more detailed, you know, explanation of what I just talked about, check out Paged Out issue number 2 and look at my article identifying crypto functions where I talk about this. But anyway, so let's just, you know, quickly confirm that this is in fact RC4, which would mean so this is a pointer. So this is the like a state pointer, and this thing here would be the RC4 state. And this is just like a counter. And then we can actually bring up the Wikipedia article. So there's a question here. Have you ever used Ghidra? If yes, what do you think of it? I have used Ghidra, not a lot. I've used a little bit. I think it's great that there is such a tool for free out. And it is very powerful, like the compilation, and like it supports like a lot of platforms and so on. I don't like the interface. I think it's like clunky, and yeah, I mean, part of it is because I'm of course more used to using IDA, so it's some part of it is just like experience, but I think it's like slow and clunky. So yeah, basically I think it's absolutely fantastic that Ghidra exists, but I personally prefer using IDA. But I mean, there's also like a huge difference in cost there as well. So like for like, you know, it's hard to beat value per money when it's free, right? And it is a good thing. So yeah. Hey, do you know Live Overflow? Yeah, a little bit. We chat and occasionally. So you should, I mean, if you don't know who Live Overflow is, you should check out this channel. But I kind of assume that if you're watching me, you do know his YouTube channel. But for other people watching, it makes a lot of great videos. So here we have the description of, actually, let me increase the font size a bit again. As I said, RC4, first we create this table, 0 to 255. Then we do this swapping, where we take these indices. I is just a counter, and j is calculated by taking one of the current value of j plus one of the entries plus one value from the key modulo 256. So we get two indices I and j, and we swap those two entries, and we do this 256 times. And then you get to the actual like stream generation thing, where you calculate these two indices I and j, you swap them, and then you use the elements as indices into the table again, and like get a byte, and then you use that byte an XOR with the target. So what we're looking at is here, let's see, this one is just the remaining count. So this is also the RC4 state. So this would be, I mean, since this is going from high to low, this whole expression goes from low to high. So this is this like SI in the Wikipedia article. And then you get here we have some rotation going on, however. So is this like a slightly modified RC4 variant? So this is something you have to look out for, because in many of these, like if you have something that, like this, which where you do some kind of like obfuscation or encryption or something, people may throw in some, like, you know, they might do like a small twist on the cryptographic algorithm. Now, of course, that modified version might no longer be secure in a completely like cryptographic sense, but typically it doesn't really matter, because in practice you will probably not be able to like crack it anyway. So it's a good way to throw people off when doing this. So you really have to kind of like make sure that even if it looks like an RC4 or something, you should double check that it is indeed. But we might not necessarily need to like understand the full details of it. We can maybe just make sure that we understand the how this like what these different pieces are and how they're used, like how are these arguments used. For example, if we look at this, in this thing that looks like the key scheduling step, it is referencing this A1, which would then be the key. And then down here, they are XORing the value here, which would be the ciphertext, or like this is an algorithm where like RC4 is a stream cipher, which means that the encryption and decryption algorithm is the same, since it's just XORing with this output stream. So this would be like the source, and this would be like the length of the data. So this means, so we call this like RC4 modified or something, crypt. And then we don't care about the details at the moment. If we have to care about the details, we can, you know, we go back to this later. So basically what's happening here is it looks like we're using the output of the verify license thing to decrypt the contents of this whole disk block here. And that it makes sense, right? And then it also, so let's call this like key 1, and then just call this one like key 2. It also looks like, and then it does this like setup MMIO proc thing. Is this actually referencing? No, it doesn't look like it is. Anyway, it also looks at this thing here, which is like, so after this huge disk block, there's another slightly smaller block here, which is just 354 bytes possibly. So this is like some ciphertext 2, and then this is like ciphertext 2 length. So let's check what this is. It says that it's a 162 hex, which is 354. So this says that it's 355. Okay, it doesn't really matter. It's probably 354. No big deal. So this is decrypted, used here, and then we sleep, and then we call this related to the memory thing. And what does this thing do? It takes this decrypted thing and a number. Okay, here it will write something to the console. So this is standard out. Well, this thing like print 2. And then it sleeps. So yeah, so this is like, it's like print slow or something. And here we call this MCI send command, which I don't know exactly what it's doing. And it's, I guess this is like the message 804, which I also don't know what it is. And then it will exit. Okay, so yeah, that seems good. So basically this thing should actually return a pointer to byte. That makes more sense. So let's just fix these signatures. Okay, so now we kind of know what we are expecting coming in and out of these. So so the next step would be, so this is the end of the verify license function. So we have this big switch thing, which goes through all of these I guess we could do a little bit of like just a poor man's thing. So first, I will say that actually I think like the proper way to do this, I was actually, after the last stream, I was actually sent an article by Antonio, which talks about this, like transparent deobfuscation with IDA processor module extensions. So here it explains how we could implement something like this, where I don't think this is like the exact same setup, but it's essentially something like this, where you have one instruction like standing in for another instruction. And we could like do some like IDA Python scripting to kind of like replace this and like properly deobfuscate this. But I actually think that it's gonna be enough. I'm gonna start out by just guessing that it's gonna be enough to just do kind of like a poor man's version of this and just making sure that we like comment which one of these is which, and then I think it's gonna be fine. So if we just name these functions after which index they have in the table, we're gonna super quickly be able to jump between them anyway. So it's no big deal. So if we go back, if we just copy this table, that's what I want to do. I missed it. Here. So we just copy this, bring this into our editor, just do some reformatting. So the offsets would be something like this. So we have, yeah, we can rename them as we go. So the first one we want to look at is this final one, which gives us the return value. So this is index 3 in this thing, which is what I have called func2 dex3. This one, so should call this like function index 3. And okay, there's no obvious indication of what this is doing. This whole shuffling around of these values, it feels kind of familiar somehow, but you know, let's keep going. No, actually, now what we should do, we should look at these. Oh no, this was a mistake. I said func2 dec3. This is this one, and that makes much more sense because it's different. So here it's doing something. So it's like looping through the whole license key again and doing something. Some rotation here. Okay, don't know yet, but let's see where this thing is used. Oh, is this finally where we use the value (407 OB6). Let's check in the thing I talked about, the constant, which will be decrypt to one thing or the other, which is at 407 B6. Yes, so this is what I in the other thing called magic one. So this thing we have calculated. Go back to our Python code. Actually, I'm gonna comment this part out to not overwrite any files again. And I'm just gonna run our code again. Actually, let's not print out all the decrypted code. So these are the two possible values. Actually, let me put this here. Magic 1A, magic 1B. So we can actually put here that it's gonna be one of these two values, and then we XOR it with this. So this is actually interesting. It looks like so this it basically looks like we're taking some kind of hash or checksum or something of the final license thing, and then we're XORing this with one of these two values, and we return that as a key. So that would indicate, if that's the case, basically it means that like the license key in the end, whatever it is, when it's put through this hash function, has to produce a specific value for this to work. Interesting. A very nice find. So what could that be then? So we had a few other functions which had like slightly different behavior. I think this was not one of them. I think it was these two, func2. Yeah, okay. All right, we had this horrible thing, func2 dic1, which is index 0, func index 0. And then we can actually put this one as like func index 1. And let's see, do we see if they are used? You can see that these values, those two functions are not called. Like if we copy this whole switch thing, we just copy all the invite things. And you see that we call all the functions from index 4 to hex 15, which would be index 21, right? Yes. So these functions are called in the switch statement, and these are not called in the switch statement. So that's also interesting. Or at least in this, not in this switch statement. So where are they called then? Here in this thing, which is on index 1. Oh, sorry, this one. This function is on index 2. And it calls the one on index 1. And then you have the whole same big switch thing as well. So what I think is going on here, that my guess is that all of these functions, like 1 to 18, will have something like this in the beginning, where they're just swapping stuff around, and then there's something else going on with these other functions. So let's just check that. It kind of looks like it has the same format. Same thing here. Same thing here. Yeah. Okay. So I mean, I'm still not looking at specifically what these different swaps are doing. It could be that this represents some it could be just like some random permutation or something, or it could be something like some kind of matrix operation or something that we know, or yeah. So not sure yet, but it looks so far that all of them really follow this same structure. And then we have this nasty thing with a lot of these XMM like instructions. And we have this like thing that looks like kind of like a random number generator. Oh, this is interesting. It's like picking. Yeah, we will have to look again where it was called. It was like, it's because it's doing this modular 18, which makes me suspect that it's like picking one of these 18 functions. So, right, so we look here in this function. It looks like this is like a countdown, a remainder, and then here we call function 1, which is this like kind of like a very simple random number generator. And then we get this. It will update the state. So this is the input. This is like the state of the generator, and then it will give you this value back, and then it will use this in the switch statement to call one of these functions, and then it will do this 256 times. So let's just see what kind of start value we get here. Okay, that would be the first argument to the function. I mean, again, the decompilation here is a bit messed up thanks to these like incorrect instructions. And it has another argument. Maybe you should just redefine this. Yeah, so here we see the references to these two. Okay, so A2 will be pushed. Okay, so it looks like this would be the the seed for the random number generator, and this would probably, but not completely necessarily, be the license, depending on how it's used in those other functions. So it will get one of these value based on this initial seed here, and it will run this loop where it will pick these between these 18 different functions. It will call one of those functions, which will shuffle the entries around. Yeah, so that's the argument to this function, which kind of indicates that since this A2 thing here is pushed could there be two arguments? But either way, this is probably the license key, because it is then passed on to those one of those 18 shuffle functions. So the question then is, what did we say? When was this function number 2 called? All right, it's called here in the beginning. So first we call function number 0. Oh, which is this messy thing here that we don't know what it is. And then we call function number 2, which will do this whole shuffling around in a loop. And then so what are the arguments to these functions? So the 0 is called with the license ID. So this is the license ID. And then number 2 is called with this variable, and also the return value of the previous function. Interesting. So which variable is this? It's just this. I mean, I would like to think that this is the license key, but I'm not completely sure. We could probably check that in the debugger. So that would kind of indicate that So what I'm a little bit confused about now is that if we so inside of this when we call this function 2, which does this looping, in each iteration of this, it will call one of these functions, one of these 18 functions, and inside of those, it will do this shuffling around thing. But then that in itself will call one of these functions. So that would be a lot of function calls, which doesn't really make sense to me. Or maybe it's because this thing will not be set. So, oh, maybe that's the case. So this thing is 0 initially. Yes, okay. So inside this function 2, no, sorry. In each of these function calls, we will do this shuffling, but when we get down here, this whole if statement will just be skipped over. So it's actually just those 256 calls, and then afterwards it will be this like recursive thing with these switch statements. So that's a little bit messy, but okay. So is it that we are here initially, this was something I touched upon very briefly in the beginning. At the beginning of this verify license thing, we initialized this array here with 54 elements based on these values like Y, W, O, B, R, G. Isn't that like... Isn't that like Rubik's Cube notation? Or maybe colors? Wait, let me check. Rubik's Cube, like algorithm. Notation. No, they use F for front. Okay. So it's not that. Fonts, back, left, right, up, down. No, it's not it. It was just something that hit me. But yeah, so it will fill up these different this array with. So this is a bit messy to read, but I think what we said is that it will start. This array will be filled with 54 entries, and it will put 9 of them, 9 each of them. So we start with the last entry, and so 9 times we will have this be 0. So it will be from the end it will be 9 Ys, 9 Ws, 9 Os. So from the beginning it will be 9 Gs, 9 Rs, 9 Bs, 9 Os, 9 Ws, 9 Ys. Which, oh, so Antonio says you are on the right track. Yeah, so maybe it is related to some some game or something, which, I mean, that could make sense. Like that is it could be something like it's a little bit silly, but it could be something like the license ID acts as kind of like the random number generator, which sets up you know, an instance of some game, and then the key has to be like a solution for that instance, or you know, could be something like that. So yeah, comments about colors, exactly. RGB, yes, could be like, I don't know, yellow, white, orange, which could be, I mean, it could still be, wait. Maybe it is, in fact, Rubik's Cube. Those are the colors of a Rubik's Cube. You have red, green, blue, yellow, white, orange, and you have 9 of them each on each side. Yeah, okay. So I might be correct for the completely wrong reason. Although I maybe there was something subconsciously about like 9 and 54, like I don't know. So that is very interesting. So you know what, like whether this is actually a cube or not, let's phrase everything in terms of that. So this is our cube, and these are colors, and this is like the color index. So okay, so in that case, why? So would that mean that each of these 18 function corresponds to, are there 18 moves on a Rubik's Cube? You have 6 different faces, which can be, you can turn in 2 directions, and then you have all the middle layers, which you can turn. Those, there would be 6 of those as well, right? Which you can turn. And then I guess something here is redundant. Mathematics. Is there 18 somewhere here? No, but maybe. Okay, anyway, let's assume that those 18 functions corresponds to the like 18 different moves. Still thinking. You have only, oh no, right, yes, there are 18 different moves, because the center, like there are 3 different planes. So first you have how do we describe this? You have 6 faces, and all of the faces can be turned like clockwise or counterclockwise. So that's 6 times 2. And then the middle sections there are like 3 different planes because we are in 3 dimensions, and they can be turned like clockwise or counterclockwise. Yeah, so as someone just mentioned in chat, there are 18 basic moves. Exactly. So these are the 18 different Rubik's Cube moves. Okay, that's good. Okay, so what does this mean? It means that, do we think that the whole thing is then that, can I get, this is in the ESI register. I want to see where this, so what I'm thinking is that first we set up the cube here. We just initialize the cube to like a solid state. And then we take the, okay, so this is incorrect. The cube is 54 elements. Oh no, okay, it's in the wrong location. We need to say, okay, so these 54 should be the cube. And then this one, okay, it doesn't really make sense here, but essentially this part, setting up the cube, and then this part. So I think what's happening is that we're setting up the cube and then calling the this function here, which I think just like mangles the license ID somehow. Also using okay, not exactly sure what's going on, but I think this will just be some kind of random value, which will then be used when we call function number 2, which will perform 256 random moves on the cube based on the seed value, which I think is based on the license ID. And then we will go through the license key. And the license key will then, so as we saw in the beginning, the license key, it was like modified a little bit. I think they subtracted some stuff. We will have to look into that. But basically, the license key should then be the solution, I guess, to the cube. And then at the end, we take the cube here. I'm going to assume that this is the cube. And it does stuff. So this is some kind of hash value or something. So basically it will take this cube and like hash it down to some value, which will be hashed with this or this constant. And then that's used as a pointer to the decryption key. So we should be able to test this hypothesis by just temporarily, like if we just think about like that this should be I mean, essentially you could probably just patch out the whole shuffling step. So like if we go directly from here down to here, we should probably get the same result as if we had a working license. Now, of course, this will not actually be a solution to the problem because we need to actually come up with like valid solutions to this. But it could be a way to like test all these things that I've been saying so far. So yes, should we do that? We could try to just reason a little bit again about what this hash function is doing. So we take the well, it's this like one cell, and this is like a this is kind of some state, and this is like some hash one. And then this is just some, I don't know, value we don't know. I mean, it looks kind of reasonable, and it's saying that for basically what we're doing here is, so this thing will only happen wait, if this is a multiple of, exactly, so if this is a multiple of 9, this thing can happen, but not on the first run. So we kind of go through this like phase by phase on the cube. We get the current value of the cell, we XOR that into the state, we decrement this, and then when we have done that for one full phase, we do this where we mix things up by taking so the high word of X is the high word of hash. So we keep the high word, but the low word is the current state multiplied by this hash, and then we put this back into hash 1. Interesting. But this means that or to me this means that this will always be 0, because this starts out as, this is a 32-bit value where the two most significant bits will be 0, and since we keep that, because we take the two most significant bytes, we save them in X and we store them in X here. So it should only be affecting the lower 2 bytes. But okay, sure. We go through this, and then here at the end, we rotate it left 16 bits. And then we negate the lower part of it. Kind of makes sense. So what we could try to do actually now is just assume the cube is in the correct state, calculate this hash thing, and see what this value is, and see if it like makes sense. Yeah, that should be pretty quick. So first of all, let's just copy this as like a reminder while we re-implement this. So this is, we call it like the cube hash from our cube, and we say that the hash is 1, and then for it's counting down again. Okay, we should actually we'll just implement it as written, or while this is bigger than 0, and then we also should have this state, which is 0. So if this current remaining thing is 0, or no, and state is not 0, then what we do is we take x, which would be the state multiplied by the lower 16 bits, this #1, and then we just mask out the higher bits. And then otherwise, we will take the state and we will XOR it with this next element. So this starts at 54, and then we subtract this remaining thing here. And then this v6 is rotate left of the #1, 16 steps. It's a 32-bit value. And then we take this result, which will be the higher bits of this will be just the higher the high bits of v6, and then the lower bits will be, we take v6 and then we negate this, and then yeah, this is a bit messy, and then we return this. And then we should, this is not correct here. So here we can just skip the x value and just say update the hash again directly. So now we just need to check in which order these colors were. And I said it goes backwards, so it goes G, R, B, O, W, Y. G, R, B, O, W, Y. So these are the colors, and then the cube is it will be 9 times that value, the character for each character in colors. We can just print the cube, then we can get this cube hash, which would be the hash of this cube, and we need to just take the ASCII values. Like we ASCII encode this to get some numbers, or actually we should do this here so we can print it nicely first. And then we should see what 2 possible values we get. So the 2 possible pointers are depending if we XOR which one of these two constants we XOR with. Let's see if this works. So it suggests these two. Could that be the case? Doesn't look like it, because it would need to be something, you know, within the range of the binary itself. So that does not make sense. Let's first just print some intermediate values here to just double check that things are fine. And in the meanwhile, we can actually like comment out this whole decryption thing, because it just takes time and we don't need it. So this prints out 0988, which, oh no, it's taking just the lowest byte here. So this would be this. Could it be what are those values? Nah. I was thinking maybe this is actually not the pointer to the key, but the key itself. In which case we won't know if it's right or wrong. I think we should do the thing with the debugger and just try to see if we can get this working. So how can we? So there are two ways now we can run this with the debugger. One way would be to just run the original binary with the encrypted code, but that's going to be super messy to follow what's going on. Another thing we could do is to create we could take this patch, we could patch the decrypted binary so that we get rid of the single step stuff and just patch out that whole thing and keep the control flow shenanigans. I like that idea. So let's take the decrypted binary, and let's see what we need to get rid of. We want to get rid of the single stepping. So this part needs to go. Go to disassembly. So we just, whoa, what did I just do now? This single instruction. That's not what's supposed to happen. Okay, maybe that's a bug or something, but we nop out these three instructions here, which are the instructions that turn on the single stepping. I'm just gonna save the analysis database. And then the next thing we need to do, actually, I think that's it, because we don't need to modify the exception handler anymore, because that branch of the exception handler will never be taken. So it should now be possible to just save this. And we can now copy this over to the Windows machine. Did I? So let's just copy copy these two into another directory. Oh, I already, okay. I already did this apparently. So let's just first try to run the first one, which it works running it. And let's try to run this one. Doesn't seem to work, but let's try to debug it. Maybe I actually break something by doing this. So oh no, actually we do break stuff, because the exception handler still has the it still has the decryption step in that. Of course, if we look here in the exception handler, we still have these two function calls here. So we actually do need to patch that. So we can go there and we will patch these. Yeah, these three. So we knock these things out. We save this. We copy permission denied. Let's copy these again. Move over to the thing here. Actually, we should stop this, replace this, and just try running it again. Still crashes though, but we'll see. Maybe we can see if it works, or like where it crashes. So anyway, we should be able to put the breakpoint, for example, in this address. And just let it run. Why is this not? Let's restart it. Okay. Okay, so we do get here. and it runs perfectly fine. And if we here we can see in the memory that we are building the cube. See 9Ys, 9W, 9O, and so on. Exactly. Yeah, there was a question. Why don't you put just a breakpoint out there so want to debug? Yeah, I just put a breakpoint in the beginning of the function to make sure that that at least we are like hitting the decrypted code. But this is before the first control flow stuff. So the problem now is then what's gonna happen? Like, is the first of all, I want to check that the control flow part was like actually that I didn't mess up. And seems fine. Okay. So let's then put a breakpoint where the hash thing is supposed to be called. However, this will this will not give us, actually, let's start by going to the first place where you do this control flow thing. So we get rid of this breakpoint, go here, and now first of all, we have the ID here as the argument to this function, so that makes sense. And then we can do we get the return value from this. So this could be the the hash from this what do you call it? So this like this horrible like XMM function thing that we saw, which creates this hash value. And then let's step. So this is pushing. Yeah, someone says like, I want to learn more about reverse engineering. How is your setup configured? I see you have several VMs running. Yes, exactly. So I'm using VMware Workstation with 2 VMs, one Linux VM where I do most of the analysis, and then a Windows VM where I do this debugging. You can use VirtualBox as well. It works fine. I used that for many years. And I have a shared, like a mounted drive shared between the 2 VMs, so I can like copy a file between the 2 VMs if I want to like run a program or something like this. So if we look here at the stack, we have pushed a pointer which is pointing to this value here, which is pointing to this value here, which is the cube. So if we now step forward, and then now something seems to break. Okay, so it worked the first time, but then it broke. So why is that? This one works, but then when we want to call this second function, we end up, where is this? This is in a weird place. Let me copy this value. It's like inside this random number thing, but it's not, it's like misaligned. How did that happen? Could something in the exception handler? So the question was, like, what about using the original binary with the same step setting the breakpoint? Yes. I guess that would work fine as well. Yeah, as long as we use this thing where we pass the exception properly, that should work. Like, we won't be able to read the code until it happens, but that shouldn't be too big of a deal. So we go to what are we trying to do? We are trying to get to we want to see the that we did this hashing correctly, basically. So we want to be inside of this. We want to be at this address. So let's delete these and add a, no. We want to go to here, 62, and we put a breakpoint. Just expand this out a little bit. So should be able to do no. Feels like it's either messing up completely or running extremely slow. Okay, nope. So if I remember correctly, you can add the exception numbers to the ignore list in x64 debug, and they are automatically handled. That's an interesting technique. Option exceptions, ignored exceptions. Look, this is interesting. So we should be able to just so if we do this, or we can do oh, maybe we need to give this as a decimal, or is it like no, that's not correct. Okay, it is a hex value, but without the prefix. Makes sense, because that's how all values are in this program. So we do this. Thanks for that, Antonio. The other one was this one, actually just this part. So if we do this, we save this, we might as well restart. We have one breakpoint at 504 EA4. Let's double check that this is where we want it to be. 504 B62. So that's not good. 504 B62. 504 B62, and then just run within ID. And now it's not ignoring it. We get exception, single step, and we are somewhere where I don't know. So this is not really behaving. And this is what I was like afraid of when I was when I thought about debugging this. So not sure exactly what's happening or why. So now we are in the correct location. I think. And this is pointing to here, which is a pointer a bit forward to here, where we have the cube. Okay, so there's something funky going on with the debugging, but we arrive at the correct place. Like the disassembly is not correct. Maybe it's not updating. Maybe it's not reflecting the like unpacking or whatever. It's just maybe just reading the text from disk or something. But anyway, we have this value in memory, so we can have this as a test value now. So we can copy this. So this is, we have 48 plus 6, which is 54 bytes. So up until here, this is the current state of the cube. So now, of course, this will not give us the... This is not a solved cube. So if we are correct in the guess, this will not give us the correct value, but at least we can see if we implemented the algorithm correctly. So we can step down to this well, basically the end of the function. Actually, let's go to this location here, because then we can also check what value the constant. We can easily check the this almost result and this constant. So this is the address we want to go to. Please. PA9. Here, we put a breakpoint. Yeah, so that's not going very well, but this should be completely deterministic. So if we instead put the breakpoint here and run it again with the same input, that should also be fine. So 1, 2, 3, 4, 1, 2, 3, 4. Waiting a bit. So I don't remember how many times we had to do this last time, but basically what I'm just doing now is just, for some reason, it's stopping on some of these single step exceptions, even though we've told it to ignore them. So I'm just asking it to continue. And it's freaking out completely. And it's jumping to some completely different location. Yeah. But we could still try to, maybe because this value is returned all the way up to, after we called license. So maybe it's better if we put the breakpoint there. Like, this is actually very messy. There's also also suggesting you can use the Decryption one and set the IP to the location you want to execute. Yeah, that would also work, and then like setting up the memory and stuff. But I don't know, let's try this first. Yeah, so like I'm not a big fan of actually doing debugging when it's like this, because there's always like messy stuff like this, and yeah, it never ends well. So we put a breakpoint here instead. We just continue running. 1, 2, 3, 4, 1, 2, 3, 4. So probably gonna go with a little bit more static analysis after this, because this is error prone and it's also quite boring. Okay, so the return value after running with this input is this. So let's let's move this here. So what do we get? So we get not a correct value, but also it kind of looks like the first one is the correct constant, because it's like kind of similar. And I would, if we had the wrong constant that we XOR with, I would expect this to be completely off. So what would be the issue then? Actually, what's interesting is that we are getting the correct value for the top half. So is it just that we do this? Okay, I'll have to look at the, wait, let's look at the code again. Oh, look, I'm taking, yeah, this should not be v6 here. It should be #1 EA52. Actually, oh, that is the correct value. Okay, good. So we found out what. So if we do this now with this cube 1 instead, we get this, which is definitely not a pointer, but maybe it is like the key itself. So let's look at this in the. So just to recap what we did, we ran the program in the debugger with some, and since the program is deterministic, like the same input will give the same output in this. So I provided license ID 1234 and license key 1234, which created this cube state, and this cube state hashed down to this value 7ADDEA52. And then I made sure by that if I input this cube state in the copy, in my copy of the hash function, I also get this value out. So we can actually, well, after XORing with this, so we can put in a little thing like this cube hash of our, we can call this the test cube, should be equal to, or no, sorry, if we XOR this with that magic plus this, it should be this. So, and that holds. Okay. So we know that now. We know that our cube hash function is now the same as in the program. And what that gives us is that if we hash the solved cube, and let's just comment this out, because that was, we get this value, and let's see how that's used here. It's, it is, that value is in itself pushed directly, which Right, it's not a pointer to an array. It's just used as an integer by itself. So this is the key in this like modified RC4 function. So what we could do now actually, are we still in this position? Yes, we could just replace that value with this value and see what happens. So we update this, and then oh no, it it didn't keep the window open, so we have to redo this. So set the entry point. I have a breakpoint. So we can put in whatever we want. And have to do this a couple of times. So I'm basically just trying to see if the goal is actually just to solve the cube. I mean, that should be the goal, right? And in that case, we should produce this hash value. So we get here, we modify, we take this value, we modify the return of the like so I mean, first of all, this is shouldn't be called verify license no longer. It should be like generate key from license or something like that. And then we can go here, I guess. And this is the decryption function, I think, located at AC. Is that correct? Yes. So let's see which one is step over F8. We go here, and then this whole So if this would have worked, if we look at this, let's see how this is called. This location at 407 D2. If this would have been correct, then this would have been decrypted into something sensible, which it may or may not have. And then the next step here so this is the interesting thing. How does this thing determine okay, so it uses this like IO thing to determine if everything went as expected. And it seems it did not. So this value is not correct. Which is interesting. This means we have the wrong return value from the key generation function, or yeah, exactly, the key generation function. So let's just double check the order again that I didn't mess up. So Antonio suggested, might I suggest to have a look at the 64-bit code again? Oh, I see. Could it be that that value is like if it's being debugged or not? That would make sense. So let's just try the other. I mean, let's try this value before we follow this suggestion. We restart, we run, we put in the license key, whatever. Yeah, that's actually a very stupid mistake by me. I mean, that feels kind of obvious in hindsight that that's the value you would, like, if you're just gonna get like one, it's just a binary decision, right? We're gonna use one value or the other. So what other runtime values that are kind of like binary in that sense would it make sense? Like if this was some kind of obfuscation technique or anti-debugging technique, that's basically the only thing that makes sense. So basically this constant is one thing when you're debugging and one thing when you're not debugging, which means that we should get this value and modify this. And then we just step through this. We look this, sorry, here. Still not entirely sure what this may or may not be. It seems like it didn't work, so did I make a mistake again? Uh, hmm. Oh yeah, I was gonna I was gonna double check I got the order correct there before, like the order of the colors as well. So this is GRB OWY. GRB OWY. 9 of each. And this is the value we are hashing, and then XORing, and then printing out this thing. And that was what I set here. Yeah, so there's something else that's wrong. That's annoying. Is this thing used somewhere else? Yeah, if I can do a recap about the validation process. Yes. So we have the this license verification thing. It will create this this cube, this solved cube, which looks like this. And then it will take the license ID and create like a random seed from that, which it will then use to shuffle up the cube. And then it will take the license key. And I suppose then that the license key is supposed to solve the cube problem for that for the key that has been generated from the license ID. And then at the end, it will call this hash function, which will take the resulting cube state, and it will kind of like hash this, and it will XOR this with this constant. And this constant is different depending on if you're debugging or not. And then it will return this value all the way back until the start here, where it will pass this where it will pass this to this decryption thing, which will try to decrypt this big global buffer thing using this key, which we actually think is not a byte array, it's just a 32-bit key. And then it will pass it to this modified RC4 function. Maybe this isn't actually a modified RC4. Maybe it's just it's maybe just slightly adjusted for the fact that the key is like it's a 4-byte array repeated. But yeah, it's like it's a very slightly modified RC4 thing for this special case. And then it uses this to decrypt this thing, and then we'll set up this like MMIO hooking thing, and then it will send the command to do something with it. I don't know exactly what this does, but we will see that, because the point is it returns like if it will return a 1 or a 0, and if it returns a 1, it will also use the key to print something, and then it will do something with this IO thing again, but if not, it will go to this thing where it just prints fail. So, but this tells me that if the goal is to get a solved state for the Rubik's Cube, because for this to work, when you have a correct license, this key must always result in the same value. Otherwise, it would not work because there's only one key that will correctly decrypt this. So I'm thinking that if we would just manually, we'll just ignore whatever, whatever the license thing is actually producing from my input, and we just replace the return value with what I think is the correct value, then this should decrypt correctly, and this thing should succeed, and we should get here. But it looks like that didn't happen, and the question is like, was that a mistake by what? Like, did I do some small mistake, or am I doing something wrong? So I should just look again that I'm not, doing a mistake in my code here. We are taking this cube. The cube. We can even be specific and say solved cube. And call this then solved cube hash. And we have this kind of like test vector that we got from running this with a some value here. And note that here we're using the incorrect constant, but it doesn't matter because the incorrect constant was also used when running this in the debugger, so they cancel out. So this this thing verifies that this code is correct, and the code really looks correct as well. Like, we have reason to believe that it is correct. So it should be possible to just take this value that we get out and just using in the debugger replace it when this hashing thing returns, and we should get the correct decryption. So I want to try that again and just double check that I really didn't make a mistake. I accidentally added another breakpoint. Okay, now I messed something up by doing that, so let's start over. We're running again. Still not sure why I have to. Okay, so now it returns. So now we see that the return value here in the EAX register, it is this test value, which corresponds to this 1, 2, 3, 4 input. So that's all good. So now we should be able to just take this value. We copy this. We modify the register. We see that we have this value modified. It's pushed to the stack, and now we see here we push the 3 arguments, or sorry, the 3 arguments to the decryption function. So first we push the length of the of the ciphertext. Then we push the actual pointer to the ciphertext. Here, starting with B9. And then we push this, what we think is the key. And then we call this decryption function. And we get something which is seemingly random data, but I mean, I still don't know what this is supposed to be. So of course, I have no idea. But it doesn't look like, I don't recognize it as anything specific. And then when we call this other function, which is supposed to set up this IO thing, we get 0 as a return value. And then it jumps to this thing where it says that the inserted license is not valid. So there's obviously been some mistake somewhere. So now how do we figure out what happened? Is the cube supposed to be... I mean, you could represent a solved cube in... You could have any permutation of these values. Like, I mean, it's... I don't really see why it would be that, but of course you could just say that the initial state isn't actually like the solved state, but it's like... I mean, you could have any permutations of the colors could be considered solved state. So for example, like, would it like RGB? That's because that would be another way to order them. So we could have any of these like 6 factorial permutations of the colors could equally as well be called the solved state. So the suggestion is like, what about using the decrypted version for debugging, setting EIP to the function computing the hash and passing a resolved cube? Yes. I mean, the question is like, why, if the hash is correct for this like scrambled thing, because we're not only trying to get... I mean, it's one thing to get the correct hash to kind of like decrypt whatever this thing is correctly. But it's a bit messy to set up in the debugger as well. And let me just actually also make sure that I really doing this in the right order. Like it will start out by it will take the first index and put it last. So y will be last. Yes, okay, that is correct. But yeah, I think that is true. We should try to just put in a solved cube now. So then we would take this other version where we have all the code decrypted. We would go to this function at this address. And then we need to set up like the stack and this global value. So let's see, what is that value? It's this value down here. Can we modify this? So this would be, let's convert this now. So struct pack little endian and then hex. Okay, so this is the value that we would need to, oh, actually we should mark this whole thing here, edit, and just didn't. Can I type it? Okay, EE1A AA7F. AA7F. So we have this value here. So that's the constant thing. And now, of course, we also need to set up the argument to this, which it only requires one argument. So I guess we can just go up a little bit on the stack, and we put a solved cube there. How many bytes is this? It's 48. This many bytes. We can edit this. No. Oh, actually, let me double check another thing. Are all these? Yes, they are all lowercase. So there was nothing wrong about that. Okay, and then we take this address, copy address, and then we go down to the stack here, and we can say like push d word. We push this to the stack. Oh no, that's incorrect. We need to push. It needs to be the second item on the stack. Like the stack is completely broken. Like if this tries to return now, it will completely break. But it doesn't matter. We don't want it to return. So now I think we should have set up all the values that we need for this function to execute. So it's looping. Okay, so let's set the breakpoint down here. Let it run. Okay. So we can just copy this intermediate value, which is not the final value, by the way. This is corresponding to this like #1 value. And then we do XOR. We copy the value. We get this value, which definitely looks familiar. Yes, it is the same value. And then this value will be returned. So this means that we are doing the right thing. So is this actually not the properly solved cube then? Or yeah, now I'm actually really worried because I don't really know what's going on here. Because that is indeed the value we're getting out, like when we did this statically, and it is the value we get out when we run this dynamically. But it doesn't properly decrypt. So that would like suggest to me that like the order of the colors are wrong. But how would you? Is there like a standard order? Here they say white, red, blue, orange, green, yellow. I wonder if this is like, but maybe the ordering is arbitrary. So Antonio is saying your test is correct. I'm checking why it's not working. So did I potentially uncover some kind of bug in this challenge? White, red, blue, orange, green, yellow. Yeah, so that would be unfortunate if there's a. So I'm wondering, for example, like very often, like why is this not like RBG, for example? So that could be one thing. I mean, we could try that in the meanwhile. But here they say, if I Google this, is this? Or if I Google like Rubik's Cube again, is it? Or even if I Google this, WRB OGY. Is this the standard ordering? No, I don't think. Yeah, so do we possibly have an answer from Antonio why this is not working? Because now it's kind of difficult how you would. I suspect that like the colors could be in the wrong order, as I said, but in that case, the logical thing would be to test all the like 720 different permutations of this. So it says that the hash of the resolved cube before the XOR is indeed 6B889478. Yes, that is what I got before before the hashing. Sorry, before the XOR, and then you XOR with Cafe Babe, and no, sorry, you don't XOR with that. You XOR with this and this, and to get 14228E96. So yeah, so we're doing some live debugging of this challenge. And so yeah, sorry everyone for that, but you know, this happens. Let me double check the other value that we had. It's in here. It's this. It's this value. This B5 54A050. B5 54A050. Yes, exactly. So yeah. In the meanwhile, is there like anyone who has any questions about any part of this so far, or of course, even if we get this now, this is actually not the solution, as I said. So what we would have to do is to actually like write the solver for this, because right now I'm just sorry. What about trying a valid license because you solved all steps? Yeah, we could. I guess we could do that. So does this mean that there is some kind of bug in the challenge? Yeah. Well, let's do that. Let's pass me a valid challenge just to see if you know what's going on here, and actually we should. Okay, so should I just run this in the like in the terminal, or should we actually try to debug it and see, or should I just? Do we want to see what hash comes out of this, for example? Yes, I think we want to see that. So we open the original binary. Okay, in the terminal. Okay, let's just do that then. We do this. We copy s4tan, and then a license key. Oh, maybe I should not have pressed backspace. Nice. You can't wait. Let me. Let me see if I can put on some. There's some nice music playing here. Can do this. Yeah. Okay, there was more to it, but there was some really nice music playing. Hope you heard a little bit of it. Yeah. So now I want to know why we should put the breakpoint right at the entry point, like the thing where the way I did to get the test value. So this is the last thing we're going to do today on the stream. I want to check what cube is passed into the cube hasher when we input this. So let's go back to the this function here, get this address here. We pick up the debugger. We restart. We go to entry point. We go to this address. First of all, we make sure no breakpoints are set. We set the breakpoint here. And then we run this. And then we set this. And then let's just copy this. License validation, stuff is running. We need to do a few of these continues. So eventually we should arrive in the hashing function, and we should see what a valid cube is supposed to look like. If we step, whoa. Okay, now let's see. It should be this value on the stack, follow the word in dump. And here we see WGYBRO. WGY bro. WGY bro. And this is not the same we have here. So the ordering of the color should be, what did I say? It should end with bro. WGY bro. WGY. So if we make a solved cube, with this. Oh, we actually get, and then this key reads out SATA code, or s4tan code, or satanic code, which is the same constant used in the random number thing. So this is the decryption key. So this means that if we go back to this, we remove this breakpoint, we restart the program, we go to the entry, we go back to right after the license is verified, we go this to this address here, we jump to this location, we set the breakpoint here, we run the program, we input any arbitrary license, we wait a little bit, and then we have to press continue a couple of times until we get to the breakpoint, and then we should get, so now we should be able to just input the this key now that we got. Even though we are not inputting a valid license, the kind of like hash of the key, this key that's derived from the license, we can just replace the return value of the function here. So we go back to this thing here, we copy the value, we replace this, we step a couple of times, and now we can check this thing in the dump, and now you can see that this is like a header for a wave file. So now this thing looks all fine, and we are also decrypting this part, which I guess is that message then. Yes, license valid and so on. And then we can just continue, and we get I can turn on the sound again. Okay, so there you have it. The issue then was that oh, okay, so this is a throwback to Ghosts and Goblins. Yeah. So the issue here was that I was doing the correct thing, but when the program initializes the starting state of the cube, it uses the color order GRBOWY, but it expects the solved cube to have the color order WGYBRO. And therefore we get the wrong cube hash, which is the wrong key, and it doesn't decrypt properly. Now, I think the only way to like realize this is to basically try, so you could like automate this, try all 720 possible combinations. Like first, of course, you have to assume that the solved state is like all the colors, like all the cells in one colors are in sequence. And then you would automate this, you would try all 720 combinations of this, you would realize that this is the color combination that it's supposed to be. And then we have now created this, we know what the kind of this problem is, that we need to create a license ID, which creates this random number thing, which will scramble the cube, and then your license key will correspond to those moves, which will bring it back to this state. So I will not be doing that part. I think this is a good place to end this, even though it's not completely done. I will maybe, maybe I will do this off stream and before I publish my script. But basically, it's very simple. It's just look at these 18 different functions, figure out which one corresponds to which kind of Rubik's Cube move. And then, of course, you also have to do a little bit of reversing of this this function here to figure out how the license ID is like hashed down to the seed for the scrambling. And then you just perform the scrambling, and then you apply standard Rubik's Cube algorithms. They're probably like ready Python libraries or something for this. Yeah, you produce this sequence of moves that will solve the cube into this state. And this is your license generator. So, yeah. That's this challenge. If you want to, as I said, I will publish my solution scripts. I will see if I maybe finish it up and then publish it. And then, of course, if you want to try this challenge yourself, check out Antonio's Twitter or the GitHub page. And yeah, just be careful that the intuitive order of the colors is not actually what you're going for. So I think that's the only critique of this challenge I have, is that I think these should have been the same. But of course, you can figure it out. I mean, like, if you just automate it, like 720 combinations it's not that much if you automate it. So of course it's still solvable. It just like adds like a little bit of like an unnecessary step, I think. But otherwise I think it's like a great challenge. We have this like nanomites thing, and this this anti-debugging trick, this jumping between 32 and 64-bit code, adding this like Rubik's Cube as the license mechanism. So yeah, okay, yeah. So Antonio says that this is a bug. Okay, cool. Well, nice. And yeah, so thanks everyone for watching. If you want to see more of these streams, please subscribe to my channel. Also, if you have any suggestions for challenges that I should look at, please send me a message. You can send me a message on Twitter, for example. My DMs are open, or send me an email or something. I would say that this challenge is maybe like towards the more difficult end of the spectrum of what's like reasonable to do on a live stream. This has now taken 3 sessions for a total of like 8 hours, or is it even, yeah, it's almost 9 hours in total. So that's a bit on the longer side. I think it's maybe better if we do like a little bit slightly easier things to keep it a bit shorter, so that people can enjoy it all. But yeah, that's otherwise that's it for me. So thanks for watching, and have a nice day wherever you are. Goodbye.